So thank you all for coming. It's my pleasure to welcome you to the Bradford Seminar Series. I'm Denise Mausero, professor joined between SVIA, the policy school, in the Center for Policy Research on Energy and Environment, and the Civil and Environmental Engineering department. Today, it's my pleasure to introduce Dr. Manuel Linsenmeier, who's an environmental economist. Last year, he was selected for a highly competitive postdoctoral research position at the High Meadows Environmental Institute. I know it was super competitive because I was on the selection committee, and he really stood out of the group of applicants. His main research interests are climate change and sustainable development. He's particularly interested in the costs of climate change, adaptation to climate change, and policy instruments to reduce greenhouse gas emissions. His research interests also include the effect of weather and climate on ecological systems, and the use and benefits of weather forecasts. And he'll share some of his work on that with us today. He holds a PhD in environmental economics from the London School of Economics and Political Science. His PhD thesis won the Best Doctoral Dissertation Award by the European Association of Environmental and Resource Economists. His work has been published in leading interdisciplinary journals like Nature Climate Change and economics field journals like the Journal of Environmental Economics and Management, as well as in the form of policy reports, primarily in Germany and written in German, so I can't say much about exactly what they covered. Prior to Princeton, Manuel worked at the Climate School at Columbia University, at the International Monetary Fund, and at the international think tank Adelphi. In addition to his research and policy advice, Manuel is an experienced teacher of economics and environmental science. Today he'll present his work on making weather forecasts work for adaptation to climate change, and perhaps he'll also tell us a bit about how implementation of some of his ideas might be affected by the recent planned layoffs at the National Weather Service and at NOAA. So thank you, Manuel. We look forward to your comments.
Thank you very much for the introduction, and thank you everyone for being here today. Good afternoon. Thank you for your interest in my work. It's exciting to be presenting here today in the Bradford seminar. Welcome also to everyone who's following this event online. My talk today will focus on weather forecasts, and let me start my presentation by saying that I think personally it has never been a more exciting and maybe more important time to talk about weather forecasts. And I see two reasons for that. The first one being that weather forecasts are currently undergoing what I refer to and what others refer to as a revolution. In fact, it is the potentially second revolution of weather forecasts that we have witnessed over the last couple of decades. And the second reason being that the future involvement of the government here in the US in weather forecasts is very uncertain. Let me start with the good news. The last couple of decades have witnessed a dramatic improvement in the quality of weather forecasts. This may have gone unnoticed. Indeed, there's a paper published in Nature 2015 that coined the term the quiet revolution of numerical weather forecasts. This figure is taken from this paper. We can see on the horizontal axis time, and on the vertical axis we can see forecast accuracy, forecast quality, and we can see different colors corresponding to different forecast horizons. So we have forecasts 3 days ahead, 3 days into the future, 5 days ahead, 7 days ahead, and 10 days ahead. What we can also see is the thick line showing the forecast improvement for the northern hemisphere and the thin line here showing the forecast improvement for the southern hemisphere. Two things stand out. Firstly, the improvement over time. Secondly, the convergence between the northern and southern hemisphere. We can see that the southern hemisphere improved overall, or forecast accuracy improved overall more, thereby leading to like a closing of this gap between the two. Now this timeline ends in 2014, and it therefore misses something that has been going on in the more recent period and that I refer to as the second revolution of weather forecasts. For that to understand, it's important to know that historically and also today, most weather forecasts have been produced by physics-based models. Those are models that take the physics of the atmosphere and the ocean, the conservation of mass, momentum, and energy, plug them into a model, and then simulate from an initial state the future evolution of the atmosphere and the ocean. Those models are used by most national weather agencies worldwide, and most of the weather forecasts that we consume daily come from those models. More recently, there's been an emergence of some kind of competitors, models that work in a different way. I call them, or most call them AI-based, artificial intelligence-based models. Those models take essentially the past 80 years of weather into their kind of into the model and then try to understand patterns existing in this kind of cloud of observations. And then use those patterns, the whole memory of the last 18 years, to start from a given current state of the atmosphere and simulate the future. So those are based on data, essentially, on the memory of past weather rather than the physical equations of the atmosphere. Now, those models have been around for some time, but it's only recently that they have become competitive, that they can now compete with the traditional physics-based models. There's a website that provides live updates on how they compare to traditional models. The weather bench, I've taken this figure from there. If you just focus on the left part of that figure, which shows us the performance of difference models for 2-meter temperature, maybe the most important variable for our day-to-day behavior. We can zoom in. We can see the benchmark, which is the maybe today most accurate traditional model, the IFS from the European Center of Medium-Range Weather Forecasts. Shown in gray, it's the benchmark. Below, in red colors, are shown all the new models, and in gray, some of the other traditional models. Everything that is shown in blue here is better than the benchmark. Everything shown in red is worse than the benchmark. So if you go down that list, we can see a lot of blue colors. A lot of models actually perform better than what is considered to be the most accurate, the best traditional weather model these days. So it seems AI-based models have already kind of overtaken traditional models, at least based on these verifications here. These two revolutions, the good news, I will come now to the maybe less positive news. As many of you know, there's a lot of uncertainty about the future of the National Oceanographic and Atmospheric Agency in the US that is responsible for all the weather forecasts, and the National Weather Service, which is part of NOAA. And among the ideas that are floating around is a dismantling of the agency, and there's also ideas to privatize most of its services. If you look into these ideas further, it seems there's a particular emphasis on commercialization and privatization, and I will say a little bit more about that later. So I'm an environmental economist. When I look at weather forecasts, I'm looking at weather forecasts from the perspective of an economist. So taking these recent developments, these revolutions, but also this kind of uncertainty about the future involvement of the government as motivation, in my talk today, I first want to make 2 points. The first one, weather forecasts provide large economic benefits. They're really important. We all use them on a daily basis, but we can quantify their importance in monetary terms, and we see these benefits are huge. The second point I want to make, weather forecasts rely on the public sector. So there may be limits to the extent to which we can commercialize what exists. In the second part of my presentation, I then want to look into the future and say a little bit how we can use weather forecasts to help our societies adapt to climate change, and maybe how we can make weather forecasts better so that they help us even more effectively to adapt to climate change. Throughout my presentation, I will use one framework, what I call the value chain of weather forecasts. This value chain starts with all the data that goes into weather models, observations, and ends with user taking decisions, making decisions, taking actions, and then these resulting in benefits. I'm aware that not all of us are atmospheric scientists, not all of us are very familiar with the first segment of that chain, the production of weather forecasts. So let me just briefly zoom in here. The main inputs to weather forecasts are observations. Those come from land surface stations, measuring things like temperature, precipitation, atmospheric pressure. They come from radar stations that look into clouds. They come from radiosondes, weather balloons that rise into the atmosphere, measure the higher levels of the atmosphere. They come from satellites looking down. They come from airplanes, sea buoys, ships, a lot of different sources. All those observations are fed into models. Those models are numerical mathematical models. Traditional models, and most of the AI-based models, divide the Earth, as is illustrated here on the bottom left, into different grid cells, and then simulate the weather in each of these grid cells. What they produce are model predictions. And those are, we can think of maps, essentially, which is illustrated here on the top right, detailed fields of data. So we can think of all these grid points having one value for temperature, one value for precipitation, one value for humidity, for each time step, a lot of data, different layers in the atmosphere, of course. And those model predictions in the end then are turned into something that we call forecasts, something usable, something that we consume on a daily basis, something that our smartphone provides to us. And that is illustrated here on the bottom right. This is just taken from Google Weather, where we can see that all this kind of amount of information is condensed into one symbol for a day, telling us whether it's cloudy or sunny, one temperature for a day, maybe the average, maybe a low temperature here as well, a probability of rainfall, something that's decision relevant to each of us. That's what I refer to here as forecast. Now we can take this value chain also to quantify the value of forecasts, and how we do that is usually we compare two scenarios, one in which users base a decision on forecast 1, and one in which they base it on alternative forecast 2. We look at the outcomes of their actions and look at potential benefits of those outcomes, compare those, and the delta between the two scenarios tells us then what is the value of forecast 1 relative to the value of forecast 2. We have some kind of counterfactual. The easiest way now to find out how large the benefits of forecasts are is just asking households. And this is done regularly. It was most recently done in 2024. That's a study that I'm showing here. And it's maybe worth pointing out that in the beginning of that survey, households are first explained that everything that they pay for here, are asked to pay for, to state how much they're willing to pay for, goes not only into like the final forecast, but also into the infrastructure. So it is also used to pay for all the satellites, all the radar, and all processes that happen after these observations are collected. Households then are asked how much they are willing to pay, and they indicate in this survey around on average $900 per year. If we aggregate that using some sampling weights to the whole of the US, we end up with benefits of $102 billion per year. The benefits that households say they get from weather forecasts. Now there's two important caveats when one looks at this, especially through the glasses of an economist. The first one is we're assuming that households know the benefits that they get from weather forecasts. If I think of the benefits I get from looking up the weather on my smartphone, it's very hard for me to think to kind of how much they're worth to me. So we assume they know of them and they give a very accurate estimate. The second assumption is that they actually tell us their true value, because this is a very hypothetical experiment, and they may very plausibly state higher values that in practice they're willing to pay than if they really need, it has consequences, essentially what they say. So those two limitations are motivations for economists then to say, well, maybe let's not only do an experimental approach, run a survey, but also look at behavior in the real world. Let's use some kind of observational approach. In the next couple of slides, I want to show you 3 examples where economists have used an observational approach to quantify the benefits of weather forecasts. The first study, done by colleagues at Columbia University and the University of Arizona, looks at the effect of forecasts on reducing mortality when there's extreme heat. So what the researchers do, they collect data on daily mortality at the county level, all of the US, over a 15-year period, and then they look at actual temperatures and forecasts on each of those days. And they look at the statistical association between realized temperature, temperature forecast, and deaths, essentially. What they find, and this is illustrated here, is that the effect of forecast errors differs depending on how hot or warm a day is on the realized temperature. So we can see here different bins, days colder than 0 degrees Celsius, this is now degrees Celsius, 5 to 10, 15 to 20, up to larger than 30 degrees Celsius. They also distinguish between forecasts that are too cold and forecasts that are too hot. What they find is then on days that are relatively warm, forecasts that are too cold result in relatively large numbers of excess deaths. Conversely, on days where temperatures are relatively low, forecasts that are too hot result in excess deaths. Forecasts that are too cold have essentially 0 effect. What they infer from this pattern is that individuals take protective action. They protect themselves against risks. So on a hot day, when the forecast is too cold, I was not protecting properly for the temperature that actually occurred. If the forecast was too hot, I took protective action, though there's no effect on mortality. I was essentially protected. And the same then for cold temperatures. If the forecast was too hot, I didn't take the protective action against cold, because that's the risk here at these temperatures. Whereas if the temperature forecast was too cold, I took the protective action, so I'm protected. There's no effect of this error. How large are the benefits? They calculate that if we reduce forecast errors by 50%, we can save 3,600 lives per year. And there's estimates of the value of a statistical life, how much we value one life lost. And the multiplication of these lives saved with that number yields $34 billion per year in benefits from a hypothetical forecast improvement here by 50%. 50% is something that is not unrealistic, and I will say more about that later. That's something we could potentially achieve in the next decades. I will actually show an extrapolation on later slides. So about a third of what we saw in the previous slide, 102 billion, here we see $34 billion per year. Now extreme heat is, of course, very devastating. We have seen how many lives can be lost here. Another very devastating type of event that we experience in the US on a regular basis are hurricanes. There's a very recent study, 2025, that has looked at the effect of forecasts in reducing the damages from hurricanes. Now for hurricanes, we usually use forecasts of wind speed. That's where lots of damages come from. And then also surface flooding. They focus on wind speed, and they collect data on hurricanes of between 2007 and 2020. I think they started in 2005 and 2020. 18 hurricanes, and they look how damages, also recovery spending, and protective action taken in advance of the hurricane or the hurricane's arrival affected the damages from hurricanes. How forecast errors, how forecasts of hurricanes affected protective actions, damages, and recovery spending. They find that forecasts provided benefits to the amount of $5 billion on average per hurricane. If you look at the improvements between 2007 and 2020. So again, they look at forecast improvements. There was a large change in the National Hurricane Center, how they produce hurricane forecasts. Investments around $500 million, and they quantify the benefits of those. $5 billion per hurricane. The last study that I just want to briefly present here looks at winter weather, different weather risk. They look at vehicle crashes, and specifically the role in winter weather advisories in reducing those crashes in 11 northern states in the US. Here the authors find benefits of around $190 million per year for those 11 states, coming from these winter weather advisories, which, and they can show some evidence for that, incentivize drivers to shift activities to different days or change their travel routes. All of those studies look at behavior in the real world. They all look at the US. What about international evidence? In some work in progress with a variety of co-authors, we collect in total over 150 studies in a systematic literature review and look at the benefits of forecasts in all those studies coming from different countries. But you can see some countries are overrepresented if you look at that sample of the literature, such as the US, also India, China, and Australia. We can see many countries for which the benefits of forecasts have not been quantified. What we can also see is that the approach that I presented to you so far, the experimental approach, the survey, the observational approach, looking at behavior in the real world, are relatively underrepresented in the overall literature. That is because historically economics has been a very theory-heavy field. And a lot of the literature has been published since like the 1980s and has been theoretical, using essentially models and assumptions about how agents behave to quantify the value of forecasts. So this observational approach is a very, very recent field in the literature. Now, how large are the benefits in other countries then? We look at a variety of sectors: air transportation, road transportation, hydropower, agriculture, hurricanes, and tornadoes. We collect all the estimates in those studies. If needed, do some currency transformation, deflate them to 2020 values, and then we can now scale them to the size of the US economy so that we could put them in relation to what I showed you before. One can see that these values vary quite a bit from study to study, All those studies make different assumptions. They come from different countries. So here I focus on the minimum and the maximum for each of these sectors. If you look at those, we can see that for air transportation, for a country of the size of the US, annual benefits have been estimated to be between $0.6 billion per year, $2.7 billion per year. Road transportation between 0.2, 3.8, agriculture 0 to 16, and hydropower 0.1 to $1 billion per year. Similar order of magnitude, we can just list them all here. I will not spell them out all, but you will see that they all are in the order of magnitude of hundreds of millions or billions of US dollars per year. Those are the benefits of forecast. Now, what about the costs? How much do we actually spend on weather forecast? And we can look at the budget of NOAA and the budget of the National Weather Service, which is part of NOAA, which are $5 and $1 billion respectively. So we can certainly conclude that the benefits of weather forecasts in economic terms are much, much larger than the costs. So what about commercialization of all the activities of NOAA and the National Weather Service? Economists generally like markets because they can lead to an efficient allocation of resources. However, economists are also very familiar with conditions under which markets fail, market failures. And unfortunately, weather forecasts are an example where we can see a lot of market failures. And we can use the value chain again to kind of locate them and try to understand those market failures. If you start with observations and models, those have high fixed costs. So for the observations, we need to think about the infrastructure that I showed before: satellites, surface-based stations, sea buoys, some coming from radio zones. Very high fixed cost to set up this infrastructure and maintain that and collect all the observations on a routine basis. If you think of the kind of at least traditional physics-based models, those are run on some of the fastest computers in the world. So very high fixed costs again to set up this infrastructure. What this means is if we commercialize those parts of the value chain, there's a risk that one large company essentially builds a natural monopoly, or several companies in different segments of the market build monopolies, which would lead to some kind of excessive profits and a potential under-provision of weather forecasts. That is the reason essentially why historically most countries in the world have decided to kind of have that under public ownership, that part of the value chain. If you focus on the final product that we consume, forecasts feature non-rivalry. It's the economic term. That means that if I consume the forecast on my smartphone, it doesn't affect your consumption of the forecast on your smartphone. There's no kind of crowding or congestion. They also feature some kind of imperfect non-excludability. That means that because it's a piece of information that's easily shared, it's difficult to kind of sell a forecast to one person and make sure it's not passed on to someone else. This is imperfect, so it's not necessarily clear to what extent we talk about what economists say is a public good and what is maybe like a club good. In both cases, because of this non-rivalry and the partial or imperfect non-excludability, we would expect that a commercial provider essentially under-provides weather forecasts, an under-provision of weather forecasts. Now there's more market failures. We can now follow the value chain and focus on user decision actions. Also think of the different use cases that I introduced before. If you think of mortality, for example, if I don't get the heat warning from one agency, the National Weather Service, but I need to look up on the internet the heat warnings of like 100 different companies, or the kind of daily forecast of 100 different companies, that brings with it like high transaction costs. So the assumption that consumers of weather forecasts find the best forecast and consume that in all this kind of cloud of information is maybe not very realistic. So we need to assume that there will be suboptimal decisions. If you think of hurricanes, evacuation decisions today are based on the forecast and warnings of the National Hurricane Center. If you think of a future where different companies provide their own hurricane forecasts and hurricane warnings, I don't want to imagine the chaotic kind of evacuations, for example, that occur in such a scenario. If you think of vehicle crashes, there's something that economists refer to as externalities. So if I drive in wintry weather, I would actually be willing to pay other drivers to consume weather forecasts, because if they crash their car, it will affect my own driving experience. So in the end, on a free market, also weather forecasts will be underprovided, because you can't charge someone for others to use weather forecasts, essentially. What the government can do is provide weather forecasts for free, kind of subsidizing the use of weather forecasts. And that's how you would address a situation with externalities. Now, all of those are market failures, traditional market failures. There's something that's maybe even more important if you think about weather forecasts, and that's something that kind of like a society needs to decide on, but whether there are kind of equity considerations, whether we want people not being able to protect themselves against weather risk without paying for that. At least provide some kind of minimum level of service, as we do in other parts of society. When we think of healthcare, when we think of transport infrastructure, when we think of anything else that is kind of provided by the government. Postal service, we don't want people to pay for receiving their mail, correct? We want to provide like a minimum level of service. So now if it's difficult to provide weather forecasts with private companies, how about then all the kind of companies that are already operating in that market? And in fact, some are providing really accurate forecasts. This is from a website called Forecast Advisor. I looked up the forecast performance for Princeton, our zip code here, and we can see that the forecast of the National Weather Service is actually not the most accurate one. There's a few private providers that provide more accurate forecasts. This is just here temperature, the first two columns. We can see the Weather Channel providing, at least for the period that's assessed here, the most accurate forecasts. Now, if you look at this figure, it's important to take into account that the private company takes everything that the National Weather Service produces as input and then kind of refines the forecast. And what the National Weather Service does is not only providing like the numerical model predictions, but also correcting them in several stages. And I've illustrated it here. This is my own analysis. This is now weather forecast for the US. The model prediction yields an error of around 3. If we automatically correct, because all models are wrong, you know, they have these grid cells that are relatively coarse. If you cannot simulate all processes in the atmosphere, if we correct for some of these errors automatically, we can reduce that to 2 degrees Celsius. Here it's forecast error of temperature forecast. If we now use the local forecast that the National Weather Service provides, that has an error of around 1 on average, 1 degree Celsius. And that forecast also takes into account kind of bias correction from regional weather offices in the US. So the National Weather Service operates regional weather services and regional weather offices where meteorologists use their kind of domain expert knowledge for that region and feed that back to the National Weather Service, who then kind of compiles all of this and provides some kind of bias corrected weather forecast. So this is what is shown here. And this leads again to a very substantial improvement. So if you look at this value chain, essentially all of that first segment is where the National Weather Service operates currently. And it's private companies only kind of like also using observations in their own models, but only coming on top of what's already provided. I hope I've convinced you now that forecasts matter and that the government plays an important role, has to play an important role here. In the remainder of my talk then, I now want to talk a little bit about climate change, adaptation to climate change, and forecasts in that context. I will start with a study that builds on what I've presented already, the paper on heat and mortality in the US. Here we can see on the left the familiar picture. We have temperature levels on the horizontal axis and excess mortality on the vertical axis. And we can see 3 curves for 3 different types of forecasts with different magnitude of error. So the most accurate forecast is shown with the yellow curve here. Essentially like a perfect forecast, 0 error. Then we see the orange line, a forecast with 1 standard deviation error, and 1 purple line that corresponds to a forecast with a 2 standard deviation error. We can see that mortality is higher for less accurate forecasts, especially so at relatively high temperatures, which we would expect because when it's hot, the risk to die from or due to complications arising from high temperature is higher, and therefore forecasts become more important. We might want to spend more time indoors in climatized environments, etc. Now, what about kind of future projections now? Now, we need to take into account 2 things. One is climate change, The second is technology. I have shown you the two revolutions that we have experienced in the past. It is very likely that forecasts will experience further improvements in the future. So what we do in this paper is essentially distinguish in two scenarios, one without future improvements in accuracy, and one in which forecasts improve according to the historical rate. And we are currently kind of anchoring the second trajectory with expert opinions. This is just an extrapolation. We can see the historical trend here for the last couple of years in the black line, but we are kind of anchoring that with experts. I can say you some preliminary results suggest that we are doing very well with this trend extrapolation, at least if you trust experts. Now, what if we now combine this trend with projected climate change? This is shown in this chart here, where we have seen two different scenarios, the one without change in forecast technology, the blue line, and then on the right, the green line, the scenario with improvements in forecast. We can now decompose the effect on future mortality relative to the present. The first part is essentially deaths because of forecast errors. Those are projected to increase by around 2,000 per year. That is because we will experience, under future climate change, more hot days where forecasts are really important. So even if we keep forecasts at the current kind of precision, forecast accuracy, because we have more hot days, we will see more people dying from forecast errors. The second part here is the component that it's a bit hypothetical that we get to when we essentially fix forecast errors or set forecast errors to 0 and only allow temperature to increase. So without any forecast errors, how many more people will die in the future because it gets warmer? A little bit hypothetically, if we add those two up, we get the total effect, and we see that under future climate change, without future improvements in forecasts, we see around 3,800 more people die per year in these projections. Now, if we add improvements in forecast errors, we see that number, that final number decreases to around 1,000. And the main difference is that because forecasts improve, the first component due to forecast errors shrinks. Actually, it becomes negative. So in the future, we will see fewer people die from forecast errors than we see today. The net effect then, comparison of these two projections, is that projected improvements in accuracy will help us save 2,800 lives per year. This is only for the US. Of course, it's important to point out that those improvements are not kind of free. So they assume that we make the needed investments to continue improving our forecasts. Otherwise, we stay on the blue line. Okay, climate change is, of course, a global phenomenon. So let me at this point maybe now zoom out a little bit. And we know also that climate change will affect especially the developing world relatively strongly. This point was made very strongly by this paper in 2015, published in Nature, where the authors look at how climate change will affect growth rates of GDP in the future. So everything that's produced in an economy, and we can see that these kind of reductions in GDP growth rates, or we can think of them as economic damages, are largest in tropical countries, here in countries low latitudes, most of which are relatively poor. The main reason for that is that the effect of temperature on economic production is non-linear, and we can see that on the top right. This kind of inverse U shape, which suggests that countries that are relatively cold actually benefit from global warming. They will go up on this curve, whereas countries that are already relatively warmer than the US, Japan, and China, we see that's roughly the peak, will experience a reduction in economic output. And this is a nonlinear curve, so it becomes increasingly steep as we move towards warmer temperatures here. So what we need to expect is that relatively poor countries will suffer the most from climate change. What about weather forecasts in those countries? This is a question that I tried to answer with my colleague Jeffrey Schwade at Columbia University. For that paper, we assembled historical weather forecasts over like a 10-year period. Weather forecasts for every day, every place in the world, all grid cells in those models, from the ECMWF, so presumably the most accurate forecast that exists. And we verify that forecast with station observations. So we also collect data on all weather stations in the world and kind of compare forecast and the realization. We then aggregate to the country level and take a temporal average over those 10 years. And this is what we find. Forecast accuracy now shown from the scale from 0.2 to 1. So darker green means more accurate forecast. We can see that in the tropics we have relatively bad forecasts, low accuracy. At mid-latitudes we have the most accurate forecasts. And then again we get a bit less accurate forecasts at very high latitudes here, especially in this northern hemisphere. If you think of the map that I showed on the previous slide, the projected damages from climate change, you can see that many countries that are expected to suffer particularly strongly from climate change have very bad forecast quality as of today. Now, how does this now kind of square with what I showed you before, this kind of improvement in weather forecast historically, and also especially the convergence between the southern and the northern hemisphere? So in this paper, we also kind of replicate this very famous chart here. It is important now to say that this chart is based on pressure, not on temperature, so a variable that we don't really care about. Meteorologists care a lot about it, but we don't really care about it because pressure directly doesn't affect me. Pressure not at the surface level, but at 500 millibars, which is like midway in the atmosphere, like 5 kilometers above the surface, roughly. It also excludes the tropics, and it covers the whole world. It covers the oceans. 2/3 of length of the global surface is oceans. So what we do is essentially we replicate, but we do things a little bit different. We focus on 2-meter temperature. We focus only on land, where humans tend to live, and we include the tropics. We then don't aggregate by hemisphere, but we aggregate by country income group using the classification of the World Bank. What we find is that there has been improvement in all country income groups now. We have essentially the same figure, forecast accuracy here, time on the horizontal axis. Improvements in all country income groups. What we can see is that the gap between high-income countries and low-income countries has essentially been constant. It has not changed. There's no convergence between rich and poor countries in terms of forecast accuracy. And the differences between those two types of countries are really large. So if we focus on the chart here on the right, which shows the forecast accuracy across forecast horizons. So this is a 1-day ahead forecast. This is a forecast about the weather in a week, 7 days ahead. We can see that in high-income countries, a 7-day ahead forecast is more accurate than a 1-day ahead forecast in a low-income country. So we know the weather, if I can say we, high-income country, 7 days ahead better than we would know it if we now were in a low-income country, using these model forecasts that I just showed. Huge differences. So what can we do about it? Unfortunately, it's very important now to make a disclaimer. About a lot of that, we can't do much. Unfortunately, the weather in the tropics works differently from the weather at higher latitudes. And it will probably remain the case that we can make poorer forecasts in the tropics than elsewhere. However, having said that, there are important inputs into weather forecasts that we can do something about. And this map illustrates that. Here we collect data on land-based weather stations and then calculate the number of stations per area to make it comparable across countries. And we can see that many countries with very poor forecast quality have very few stations. They collect very little information about the weather. Now, does this information from land stations actually matter for forecasts? If there were some meteorologists in the room, they would maybe challenge me for that assumption, because just of the amount of information that goes into models, which includes satellites, which includes, as I said, radars, which includes radio zones, planes, etc. So a lot of kind of alternatives to like a station that is mounted on the ground. We can answer that question with models by running experiments where we essentially forecast the weather multiple times, but in each of these simulations, ignore part of the observations, including land-based stations. So we can do the perfect experiment and look how that affects forecast accuracy. We can just ignore stations and then put them in again and see how do forecasts compare. This is done now by continent here. This is an experiment we haven't done ourselves, but it has been done before. And we can see that yes, the number is positive. the impact of observation is there for land-based stations. What we can also see is, on the horizontal axis now we have the number of existing observations essentially. What we can see is that places that have very little observations as of today, the impact of each observation is very high. So Antarctica, where we have very few stations, the stations that we have there have a high impact on accuracy. South America, where we have still very few stations, again, high impact per observation. And we can continue down that line until we end up in Europe, where we have a lot of observations, and each observation actually doesn't have such a large influence. This suggests that eliminating some of these inequalities is actually a really effective way of improving forecasts, because we would install stations where they contribute the most to forecast accuracy. Important here also now to take into account that a station doesn't only improve forecasts locally. So if we mount one station somewhere here, let's say in Brazil, it also improves the weather forecast in the US, everywhere in the world, in fact. Because the weather that we experience today in Brazil will have an influence on the weather, will be correlated with the weather in the US, maybe in a week, maybe already today, due to some kind of oscillations which cause these kind of large-scale teleconnections. Okay, we organized a workshop last year at Columbia University where we showed these results to meteorologists from the global south, global north, and they all said, yes, stations are a problem, but it's actually not, it's not done if you just fix the infrastructure. You need to do more, and specifically you need to make sure that those stations are maintained, that someone does quality checks, that someone kind of actually processes the data, which is usually done first at the national level, and then it is shared internationally. We illustrate that point here by looking at the number of times a station actually reports, again by country income groups. So we have all the observations that have been used for forecasts in the past, and we can just count the frequency essentially and see that in high income countries, stations report on average 0.7 times per day here, which is more than 2 times as often as in low income countries. So there's these huge kind of inequalities also here. Now, it's of course not done with collecting information. Countries usually produce their own forecasts. There's good reasons for that. Models that cover the whole globe are very inaccurate if you look at a specific country. They do their best to kind of simulate the weather everywhere, but that means they have limits when it comes to like a very kind of local scale. Unfortunately, many countries don't have the capacity to do that last step, to produce their own forecast. And we can quantify that here by looking at the number of countries in these different country interest groups that actually report official national forecasts to the WMO, the World Meteorological Organization. And we can see again, high-income countries, 80% report, low-income countries, a fourth, 20%. So we are here kind of like looking at different layers of inequality, all saying the same thing. If you start with the model predictions, if you look at the infrastructure, if you look at the quality of the infrastructure, and if you look at the last step, producing forecasts, there's huge inequalities that we can do something about, at least as we move along the chain. Okay, I want to leave some time for discussion and questions. So let me conclude with some more kind of like practical insights. So in the study that I already mentioned, where we collect around 150 previous papers, we also look at what the authors of those papers found as barriers to realizing the potential benefits of forecasts. I mentioned those numbers are huge, $102 billion per year. The question is, do we actually realize those benefits? And we classify barriers here in that space in different types. We look at the provider side, and where we look at barriers related to the quality of forecasts, the relevance of forecasts, institutional arrangements, dissemination strategies. And then as we move along the value chain, we also look at the user side, accessibility, service uptake, understanding and interpretation, and the ability to act. What we then do is look at the share of studies that report barriers of each of these types across different sectors and then for all sectors together. Let me just focus maybe on the summary statistic here for all sectors together. We find that on average around 20 to 30% report for each of these type of barrier that that barrier mattered in that specific context. So it seems like these barriers really matter. If you look which ones seem to matter more than others, we find that the ability to act seems to be very important, as well as relevance of forecasts. And maybe to illustrate those two barriers, ability to act, we can think of a farmer who receives a rainfall forecast for the growing season and now needs to decide which crop to plant. They would like to plant a more drought-resistant crop because the forecast suggests there's a kind of deficit in rainfall, but they don't have the financial means to afford the seeds. So they're not able to act actually appropriately based on the forecast, which means the forecast is essentially not of much value to them. They may be credit constrained, not be able to kind of like purchase that even with some kind of loan arrangements. We can see this barrier is actually really frequently reported also for the agriculture sector, ability to act. To illustrate the second type of barrier, relevance, thinking of the same farmer, the farmer may get a weather forecast for the next 2 weeks, but actually the crop is most sensitive to rainfall in like 4 weeks from today or 6 weeks from today. But I need to decide today what I plant. So that forecast is essentially of maybe very accurate. Maybe I'm able to act. I have different crop seeds here, but I just don't have the information with the relevance that is needed here, kind of the forecast horizon. On my last slide today, I want to kind of close the loop to the very beginning and point out some, I think, questions that arise now from the work that I presented to you and the kind of developments that we are seeing in the world out there. The first one is, can AI-based models replace physics-based models in some contexts? Especially if you think of like the relevance barrier here, AI-based forecasts have the large benefit that they're very cheap to produce. So for a classical physics-based model, a forecast, you would need to have a high-performance computer, and it takes several hours to produce a forecast. With an AI-based model, I can run the forecast here on my personal computer, and it takes maybe a few minutes. So there's a large potential for forecasts to be produced much more decentralized way by many more kind of agents that can tailor those forecasts much more to specific users. At the same time, it's important to point out here that AI-based models, they work with this kind of memory of the past weather, and the past weather they take from simulations of physics-based models. So AI-based models, most models that are out there today, they actually function only because we have the physics-based models, which have simulated the weather for the last 80 years. So there's a bit of a caveat here. But if you only think of the last part of the value chain, producing accurate forecasts for users based on model predictions, there's for sure a lot of potential. The second question, can AI forecasts close the gap between rich and poor countries? I know of current developments. For example, in different countries in Africa, now looking into AI forecasts because they suddenly have the capacity to run those in the National Weather Service because the costs are so much lower. So there's potential to kind of close that gap, again, especially at the later parts of the value chain. And the last question, and that's related to the first one that I answered here already to some extent, can AI forecasts help making forecasts more relevant? Many more, of course, and I'm very happy to discuss them also with you if you're interested and maybe identify some research opportunities. Let me maybe skip the summary at this point and just express my gratitude to all my collaborators, my co-authors. I've not been able to present all the work that I've done on weather forecasts today, so you will see some faces here that didn't appear on the references on the previous slides. But everyone that is shown with bright colors here has really influenced my thinking on weather forecasts. And also thank you, of course, for your interest in this work. And you will find some work on my website. I'm also happy to answer any questions by email. And I look forward now to our discussion. Thank you.
So thanks so much for your excellent, interesting, valuable work and talk. I think it's fine for you to take questions yourself, but I might just ask a quick one to start, which relates to your very last slide on AI. And I'm just wondering, earlier in your presentation, you showed that the ability of weather forecast models to predict accurately the topics is much lower than the ability to predict in the mid-latitudes, and that there's data shortages and all sorts of other things. The best AI will be able to do is to take the data from those physical weather models and use it to predict only as accurately as currently as possible, right? And so ideally, wouldn't there be some efforts to collect additional data in the tropics in order to make even the AI models better?
Yeah, so I can, thank you very much for that question. I can maybe add two comments to that. The first one is that I think that's what you pointed out, essentially AI-based models use physics-based models. So I discussed the question about the potential of AI-based models to limit these inequalities between especially the tropics and extratropics with some expert at the ECMWF, the European Center of Medium Range Weather Forecasts, who are now actually using AI-based forecasts operationally. It's one of the first in Europe. So they've actually taken some of the kind of leading models and using them parallel to their kind of traditional physics-based model. And what they've told me, and they haven't done yet a kind of study on that, but they've told me that it doesn't look much better because the AI-based models are essentially trained with a physics-based output. So the same limitations apply. They may do a little bit better, but we wouldn't see like a similar revolution as we've seen maybe of that order of magnitude as I showed before. And the second comment is there's also attempts now to develop AI-based models that start directly from observations, not from model predictions, that kind of skip this kind of training stage using model predictions. So they are trained only based on observations. And maybe there's more potential for those models because they will not kind of be limited in the same way as AI-based models that train on physics-based models.
But you still need to collect additional data in the tropics in order to make that forecast more accurate.
That would help, but already just starting from observation could already help to some extent. Because the physics-based models have problems with just like the simulating the weather in the tropics, essentially, right. with the physics that we have. Yep.
Thanks for a very interesting talk. I'm a marine ecologist, and I wonder two things. One is relevance to the marine environment, and the second is what do you know about advancement in the forecasting of ocean weather? There's obviously much less instrumentation in the ocean, and the physics is more complicated. The second question is, what do climate scientists think would be the accuracy of the forecast at the end of the century for a month or 2 months from now? I know that more and more chaos is added to the system, but
yes.
Are there any projections for the type of accuracy we'll get in longer time spans than 10 days?
Yes, yeah, thank you for the question. So first, I should say I'm not trained as an oceanographer. I have some training in meteorology. So for me, kind of like it all ends where the atmosphere ends, like at the upper level of the ocean. In that paper that I presented to you, though, we look at observations that are collected on the oceans. And we can see here the map, not for land-based weather stations, for the number of sea buoys, which is used then to forecast the atmosphere. Essentially, they collect mostly atmospheric pressure at the top of the ocean. And there we can see a little bit less inequality if you now kind of correlate it with country income groups and take into account where those sea buoys are, where they will improve forecast accuracy. So we don't actually see a similar inequality for sea buoys. One reason is that most sea buoys that we see in the world are maintained by high-income countries, and they're floating around the world. So because there's no kind of national domains where national capacities certainly matter, like as is the case for land-based stations, we don't have such kind of inequalities. What happens in the oceans, though I'm not an expert, though I can't say much about, for example, temperature or salinity in the oceans. Related to the second question on climate change, so climate change will have different effects. It will change the mean temperature, it will change the number of extremes, it may change the variability of weather. So all of that will kind of affect the accuracy of forecasts. What we know in the US is that forecasts tend to be more accurate on hot days, so that actually helps us. What we also know is that they are less accurate if there's more variability. So if you look at heterogeneity across the US, we see that forecasts are less accurate where we have higher day-to-day fluctuations. That means climate change will it works like the other way. will make forecasting more difficult.
What I meant was that regardless of climate change,
Mhm.
extremely important, of course, will affect it. In terms of the technology, the modeling, what's the forecast of improvement? Can we predict to 80-90% the forecast in a month?
Oh, so so I think atmospheric scientists would be very kind of cautious when it comes to these very optimistic expectations. And the main reason is that the atmosphere is kind of like a chaotic system. So there's inherent limits to predictability. Having said that, if you look at the historical trend, there has been a continuous improvement. And if we ask experts, they give us a response that looks very similar to what we see here, where we see that the forecast error would decline from currently about 1 bit less, maybe 0.8, to roughly like 2/3 of that. No, how much is it? Yeah, like 1/3 of that number. So that seems to be what experts expect. Of course, we're talking here about really long time horizons, like 2,175 years into the future. A lot of uncertainty, of course. But that's what experts expect.
Another question about some of the variability points you touched on. Is the magnitude that people are projecting that the forecasts are going to be hurt by climate variance greater than the magnitude that people are projecting climate forecasts are going to improve, or whether forecasts are going to improve over the course of time? So are we going to, as climate change continues, are we going to see a point at which the variability of climate conditions, and weather conditions in particular, is going to outweigh the improvements that we're observing in technology in our forecast? And then the second part of that is when you're looking at expected improvements in health and mortality from more accurate forecasts, are those coming from actual forecasts, or are those coming also from like the nowcasts? People are checking the weather, with weather right now, and looking at the forecast. Can you disentangle those in any way?
Yeah, great question. Thanks. Both great questions. So when it comes to this race, and you see it here in the title on the title of the slide, the race between climate change and technology.
Yeah.
I think based on what we have found in the responses of the experts, technology is going to win that race. So climate change will make forecasting harder. When we only look at forecast accuracy, climate change will make forecasting harder to some extent because of larger variability. Maybe a little bit easier in some places because temperatures get warmer and that's easier to forecast. But technology is just the kind of big trend that will dominate the overall picture. Related to the second question, so when I say forecasts, I mean a variety of products kind of like bundled together. That includes the traditional 1 day ahead, 2 day ahead forecast. Even in this case, some kind of warnings or impact-based forecasts. Or we could think of like at the current kind of edge of the forecast horizon, some kind of nowcasting. So the weather in the next 1 hour up to maybe the next 6 hours. In that specific figure here, we look at 1 day ahead forecast and also 3 day ahead forecasts. So I can't say anything about the nowcasting and how it affects mortality here. We haven't looked at that statistically. The main reason is that the National Weather Service doesn't provide this nowcasting. And we are here, or at least not for temperature on a kind of operational basis. And so we are here using the official forecasts, assuming that this is what most people consume, so where we would actually see an effect on mortality, on behavior and then mortality. This is the forecast that the National Weather Service shares with local radio stations, with with television, to a wide range of kind of like local stakeholders as well, in counties that are responsible then for kind of preventive measures, for example, when it comes to like some kind of extreme heat event. So that's kind of like the main forecast that is used in the US. I've seen we've reached the end of the 1 hour. I see there's one more question.
You can take one more question.
So I can take that one last question then.
Thank you so much. The value chain model that you shared with me, I'm interested in the user model. Obviously, different users have different objectives, and not all models can be good at everything all at once. Do you ever see sort of trade-offs in the objectives of different users which these models can do well? So, for example, improving one forecast target would decrease the performance in another one of different users. How do you think about that?
Yeah, thank you. That's a really great question. Because there are those trade-offs actually, and meteorologists know about them. but it's not so much maybe publicly communicated because it's like sensitive topics. You could, for example, think of global forecast models kind of preferring certain regions of the world because the verification is done mostly for those regions, because the interest is on those regions, and therefore there would be like a model development that biases against other regions, potentially. That is to some extent the case, because most global forecasts are produced by high-income countries, and those countries usually look, when they look at the verification, of course, because they're paid from the taxpayers' money, the forecasts for their kind of national domain. So we would expect that there will be these biases in model development. I know, for example, just to give one example, that temperature used not to be assimilated in some of the global forecast models because it would negatively affect forecast performance for other variables. It does, though, improve the temperature forecast. So there's a trade-off between forecasting temperature versus, for example, atmospheric pressure or rainfall. And the question is now, of course, if you just have one model, what is your kind of, as you say, kind of target? There is for sure potential, if you go to the last stage of the value chain, with a diversity of models, maybe kind of resolving the trade-offs. So you could think of models that are kind of trained to predict one variable very accurately or one region of the world very accurately, and others for other variables in other regions. So there's a lot of potential, I think, to resolve these trade-offs in the end. Yeah, thank you.
Great, thank you so much.